As it turns out, thermodynamics is not just a theory describing what we can do to the ideal gas. It, in fact, has a much broader range of applicability. This is the lecture where we finally get to look at some other systems that we can apply our new thermodynamic methods to. We now have a lot under our belts. We know about simple systems, we know about the control operations we can do to them, and we even know about some intensive properties of systems that we can use to speed up calculations and that give us a lot more sort of conceptual clarity about what's going on. Now let's apply all of that to these new systems, which we'll introduce today. The first one that we should talk about is the diatomic ideal gas. I'll say definition here, but all I'm going to do is give you the equation of state for this system. It has exactly the same internal energy work coordinates as the monatomic ideal gas. What we get instead is NKB, same as before, log of sigma, which still depends on the material, V over N, U over N, but now that's raised to the 5/2. Furthermore, we're going to add 7/2 NKB. Now, let's do one brief calculation with this, just so that we can get some sense of what's going on. All right, so we'll find the temperature again. And to do that, we'll find the partial of S with respect to U. Now, just as before, the second term has no contribution because it doesn't depend on U at all. The first term has this factor NKB, which just comes out. Then we have log of U to the 5/2 as the quantity of which we need to take the derivative. The 5/2 comes out as a multiplicative factor as well. And then we get 1 over U from taking the derivative of log U. And this implies, again, that this is equal to 1 over T. So U is equal to 5/2 NKBT. Contrast that with U equals 3/2 NKBT for the monatomic ideal gas. And we see that to change the temperature by the same amount for a diatomic ideal gas, somehow it takes more internal energy. And that's a little bit confusing, although much later in the semester, we'll see why it might be that this is intuitive when we look at the problem from a certain angle. For now, just notice that this basically functions like the monatomic ideal gas, but it has this small change in properties. It's harder to heat up and harder to cool down. All right, let's focus on the ideal gas with two species, which really does present some qualitative difference from the monatomic ideal gas. Again, I'll say definition, but I'll just give you the equation of state. In this case, we'll get NKB log of sigma V over N U over N to the 3/2 plus, and again, let's say that this is two species, both of which are monatomic. Then we just get 5/2 NKB. And let's actually be clear that this is sigma for the first species. Now, what do I mean here by N, V, and U? And the answer is I mean the number of particles of both species, the volume of the total system. It's just one volume. All the gas molecules are hanging out together. And then U of the whole system, the kinetic energy of all of those particles together. Now, we will add some things that depend on the energies, volume, and particle numbers of the individual atoms. Actually, I guess not the volumes, but just the numbers of the two individual atoms. Okay, so we'll get NKB times the log of sigma 2 over sigma 1. Then plus NKB, oh, and I should have mentioned this is N2, NKB times x log x plus 1 minus x log 1 minus x. And I need to define a couple of things. So sigma 2 is the sigma constant for the second species. X, by definition, is just equal to the proportion of all of the atoms which are of type A. So, or type 1, I should say, n1 over n total. And it follows that 1 minus x is equal to n2 over n total. Okay, so what are all of the terms here doing? This, notice, is just the ordinary ideal gas entropy. On the other hand, this term is brand new, and it compensates for the fact that these two gas species may not have the same mass. So it turns out that sigma 2 and sigma 1 are different precisely when the gas species have different mass atoms. So we'll call this the mass compensation term. Finally, this term is also perplexing. It's called the entropy of mixing, and we won't be able to explain where it comes from until much later on in the course. But I want to introduce the notion that it maybe suggests some sort of fundamental discontinuity present in the theory. And what I mean is this. We don't have a good sense at this stage. Nothing within endogenous to thermodynamics tells us how to tell two different species of something apart. How do we know when we have one thing which is different from another thing? What is the essential thingness of atom A, or atom 1 here, that makes it different from atom 2? If we make some sort of a small difference, whatever that makes, or a small change, whatever that means, to atom 1 such that it becomes atom 2, it turns out that we can add a whole lot of entropy. And just for clarity, let's imagine that we make whatever minute change to these atoms is necessary to distinguish them from the original type. And we make this change to half of the atoms in the sample, such that x is 1/2. So if x is equal to 1/2, that would imply that the entropy of mixing is equal to nkb times 1/2 log 1/2, which is 1/2 negative log of 2, plus, well, 1 minus x is also 1/2, so 1/2 times negative log of 2. So this, again, is minus 1/2 log of 2. I'm realizing actually here that I made a sign error. This should be negative so that the entropy of mixing is positive, which it should be. Since x is going to be between 0 and 1, this log is always going to be negative, as is this log. So in order for this whole term to be positive, we need a negative sign here. In any case, if we distribute that negative sign through, these will become positives, and so we would get 1 times log 2 times nkb, so just nkb log of 2. And the fact that there's this n here means that we could have a potentially huge increase in the amount of entropy in the system, even though we've only changed things very slightly by changing whatever the essence of half of the atoms is. That must be some kind of weird mechanism, and in fact it is. It requires quantum mechanics to fully explain this. In any case, I think that this is a very interesting example for that reason and for another. It tells us how we can deal with a situation in which we introduce particles of a new type into an ideal gas system that already had particles of one type. So just to be clear, imagine that we have argon in a box, and then we introduce some xenon atoms. Our old theory told us, or it had nothing to say about how we would deal with such a system, because we only had the Sackur-Tetroda equation for the entropy. The Sackur-Tetroda equation would have only told us to increase the particle number. It said nothing about different species. Here we learned that, in fact, to get correct empirical predictions, we need to assume that before we introduced any of the xenon atoms, we were using this particular equation, which included the entropy of mixing and the mass compensation term, and we simply set N2 to 0. If we set N2 to 0, N2 being the number of xenon atoms, then this term would clearly vanish, and this term would vanish as well. We in fact need to take a limit, and you should check this on your own, in order to make this make sense. But basically, we'll take x to 0, or sorry, x to 1, precisely 1. That means that this log becomes a log of 1, which vanishes, and then we have something that looks like 0 log of 0. And what you'll see is that in the limit, this makes sense and vanishes as well. So in that case, we would just obtain the Sackur-Tetrode equation again. But once we've introduced the xenon atoms, we get a different answer. Okay, the final system that I would like to look at is called the Einstein solid, and it's our first example of a non-gas system, so I think it's very interesting and useful. Okay, so the Einstein solid is going to have the following equation of state. First of all, we're going to need an intensive constant U naught of type energy. And we'll also need to have the following two extensive quantities, U and N, on which this system depends. Now we can finally write the equation of state. So we're going to have S, and actually I'm just going to divide it by the Boltzmann constant to make this a little bit simpler and cleaner. We'll have S over KB is equal to U over U naught plus 3N times the log of U over U naught plus 3N minus U over U naught log U over U naught minus 3N log 3N. All right, wonderful. Now, this might not look like it makes a lot of sense. And in particular, it's not clear why we don't need more extensive parameters in order to describe a solid. When Einstein came up with this model, it was supposed to be able to describe many types of solids equally well. So it's interesting that it doesn't involve, for instance, the volume. It only involves the number of particles. What we actually find empirically is that this is a pretty good description of many materials at higher temperatures. Since that's the empirical reality, we should figure out what the model says about the temperature here and then figure out the consequences of that. So to figure out the temperature, let's do our normal procedure. We'll take the partial of S with respect to U. Now, I'm not going to follow through on all of the careful details here because, one, that's something I think that you should do and would gain some benefit from, and two, it would take a lot of board space here. Instead, I'll jump right to the conclusion. U is equal to 3N U naught times the quantity 1 over E to the U naught over KBT, all minus 1. Okay, so this is a pretty interesting expression. If you go ahead and plot this U as a function of T for a fixed U naught, you'll see that it has a very characteristic shape. And we'll see what that shape looks like here by taking some limits. So the first one I want to look at is what happens when T is small. And what I mean by small here is that it's small in the argument here, such that U naught is much bigger than KBT. So let me say it like that. KBT is much smaller than U naught. If that's the case, then U over KBT is going to be a very large quantity. That will mean that E is much larger than 1. And we'll be able to reduce this equation to U is approximately equal to 3N U naught times 1 over E to the U naught over KBT. Now we can move the 3N U naught over to the other side and then move E, we'll cross multiply E so that it's in the numerator and U over 3N U naught is in the denominator. Then we can take a log. At the end of the day, we find that U naught over KBT is equal to the log of 3N U naught over U. And then furthermore, cross multiplying again, we find that T, in fact, let me just give it for KBT just to make our lives a little bit simpler. KBT is then equal to U naught over log 3n U naught over U. Now we kind of immediately see a problem, which is that in various senses, this becomes singular. So in particular, as U goes to 0, this is going to blow up. And so we'll not be able to get any sort of meaningful results out of it. Now let's go ahead and take the other limit, which is when T is very, very large. If T is very large, then U naught over KBT is a very small quantity. Then we can simply take the Taylor series of E and take the 0th order and 1st order terms. So 1 plus U naught over KBT. If we do that, we find the following. So let me say KBT is much bigger than U naught. In that case, we find U is approximately equal to 3n U naught divided by, and then we'll just get 1 plus U naught over KBT minus 1. The 1 and the minus 1 cancel, and we just get U naught over KBT in the denominator. Now, a couple of things cancel here. Just the U naughts, really. And we can solve for KBT. So we get KBT is equal to 3n over U. And this gives us a linear relationship between T and U. Notice that we also got a linear relationship between T and U for the ideal gas, both the diatomic and the monatomic ideal gas, in fact. This points to the possibility that this is a pretty good approximation. That kind of linear behavior seems pretty normal. And in fact, it is. This is the regime in which this seems to match many empirical results that we see about solids. So we'll go into more detail about the Einstein solid later in the course and in a later video in this lecture. But I wanted to present here just these two limiting cases so that we could see one thing that I think is true about a lot of thermodynamic systems, which is that when we create an equation of state, we're not necessarily looking to be able to describe the entire state space of a system. Because the equations of state we work with are often approximations, it can be useful to ignore certain parts of the state space in order to make the functional form much simpler and easier to work with. So in this case, we create this form in order to really work with the high temperature case. And usually we ignore the low temperature case entirely. Now, with all of this under our belt, we're ready to look at some more control operations that maybe we can use to increase our understanding of what's going on when we work with reservoirs. We'll get to that in the next video. Thanks so much for watching.